Okay, this is going to be a video on related rates, and I'll be providing some difficult and challenging problems to help you develop a better understanding. Throughout this video, I encourage you to really give a go at the problems and try for 5 to 10 minutes before looking at the solution in the video, because that's really how you develop skills to solve these type of problems. Before that though, let's start with a small diagnostic on implicit differentiation. So before you move on to related rates, you should be able to solve this problem here pretty comfortably. As a side note, all problems in this video will be provided by a book by Stewart called Calculus Early Transcendentals, its 5th edition. Okay, let's start. Show by implicit differentiation that the tangent to the ellipse at point x naught y naught is what's given there. So let's start by differentiating the first equation with respect to dx. So you have x squared, right? So we differentiate both sides, we get, and because we do it with respect to dx, we have 0, right? Okay, we move this term to this side, we get dy equals to negative xb squared. Right? Okay, so, and we want to find out what is happening at point x naught y naught. So at x naught y naught, all you have to do is plug in x naught y naught into this equation here, and you get the slope at x naught y naught. So you have and all you have to do now is use 2-point form. So okay, and you multiply both sides by x minus x naught and y naught a squared. So what you should get is alright, and by rearranging the terms a little bit and making all the common denominators a squared and b squared, you should get hold on, x times alright, so now we have this, right? All we have to do now is we can see that this equation matches this equation very closely. Formula for an ellipse, this side always has to be 1. So our final answer is x naught over a squared. And that's our final answer. So now pause the video, try to solve this problem, and I encourage you to draw a diagram for each of these. A diagram really helps. The hardest part about related rates is essentially determining what the equation is and what you're trying to solve. Everything else is just pure algebra, and it's pretty easy. Alright, I'll give you some time to solve it. Here's the solution. So let's draw the diagram out first. We have this as the pole, this should be 15, and this is the human, which should be around 6, right? And what we want to find is the tip of its shadow. So at rest, the shadow comes around this point, right? We have a right triangle here, that's right. But however, the person is moving. And the hardest part about this problem is identifying the fact that as the person moves to a different location, let's say here, the shadow also changes. And that's our new point there. So the change of the new shadow point, or the new shadow point, is dependent on the speed of the person and also the change of this original shadow to this shadow right here. That is the change that's the change of shadow. That's a change in the length of shadow per second, basically. So now we just assign some variables around. So let's say this part we assign as x, and this part we assign as y, all right? Now you have to use some trig here, and you have to recognize that this triangle here is similar to this triangle here. So we have x plus y 6, right? This length to this length, and this length to this length. Let's multiply it out. Oh, sorry, not 15. Alright. So now we also are given that dx over dt equals to 5, right? This is the speed at which the person is moving. Alright, so now let's rederive this again. So right, and we know this is 5. So okay, and we previously established that this change is dependent on the speed of the person and the change in shadow per second. So all you have to do now is you just do dx over dt, and that is 5 plus 10 over 3 equals to 25 over 3, and always put units, feet per second. And that's the answer. So as you might be able to see, the hardest part of this question was not the calculus. The hardest part was defining what was constant, what is always changing, and really finding an equation to define that. All right, let's move on to the next one. Okay, let's tackle this one now. Pause the video now, take some time to solve it, and come back either when you've solved it or you're stuck. All right, as always, let's draw our diagram. So we know ship A always starts 150 kilometers west of ship B, right? This should be 150. And what we're finding is the change when A is at 25 kilometers an hour and B is 35 kilometers. So A is traveling here, A is 35, yeah. Okay. And B is traveling at 25. We know that they are both traveling for 4 hours, so A's final position will be 150, and B's final position will be... Okay, so let's draw another diagram to represent what's happening. This is what's happening at 4 o'clock. This is 4, and this is 12 o'clock. And let's define this length as L. Okay, so what we know is always constant in this question. Well, we know that the time is always 25 for B, and we want to find the change in L. So let's find what's the length of L at this time. So we have L equals to the square root. And plug in your calculator, you should get around 100.5. So L is 100.5 at 4 o'clock. Alright, so now let's do the calculus part. We have to use the distance formula to represent the change in L, not what L exactly is, but the change in L. So L should be equal to square root of 150 right? this is what's happening as the ships are moving and L is changing, not when it's stationary. We can just square both sides to make our lives simpler. What we're trying to find is dl over dt, right? The change in L with respect to time. So we'll take the derivative of both sides. Cancel out 2 on all sides, and what we get is L times dl over dt equals 2, and we know time is all 4 seconds. This one's 4, this one's 4, and you should get right? We also know L is 100.5. So right, and simplifying you get and your units. And so when I was doing this question, I was skeptical. Y is 21.4, B is 25, so shouldn't the hypotenuse always be more? But you have to keep in mind that A is actually decreasing this side length, although B is increasing. So it actually makes sense that the hypotenuse is less in this particular scenario. Alright, let's move on to the next question. Okay, try and solve this one. Now, I will warn you, this one has a lot of moving parts, and what I highly recommend you do is try to identify what's constant and what's always changing. That will really help you solve the problem. And as a side note, if you recognize I make any mistakes, feel free to tell me. Okay, now, we know it's feet cubed, so we know we're trying to find volume. So the equation, and you have to realize that this space here will always remain 12. No matter if the water goes up, goes down, it is always 12. The second base here, however, we don't know what it is, so we'll assign it as B for now, times the height. And this is where it gets tricky. So let's take this small cross section. So we know if the water is at max, this part is 6, and this part is also 6, right? So what can we infer from this? Well, we can infer that whatever this height is, if it's y, this height will always also be y. So let's write an equation in terms of this space here. We know it's always going to be 12, and we know it's going to be whatever that is. The height, right? Assuming this part is h. Okay, now let's analyze this section over here. We'll make it in red. So you know this part is 6 at when the water is max, and this part is 16. So the relationship right? This is the ratio when the height change when water is full. So 8 over 3. So when this height is unknown, we have this length as 8 over 3h. They do plus 8, 3h. Great, now we have an expression for our base. Okay, now I go back to the volume formula. Oh, and by the way, you have to times 20 here. I forgot to do, but it's fine. So volume equals to 20 times 1/2 times h, right? And you eventually get Alright. And from B, we know this is equal to great. Now we have this. So now all we have to do, we want to find dh over dt. So let's take the derivative of both sides. Right, we know this because we know what h is. So we know this is also 0.8. So we have and that is our answer. Alright. Take a moment to look at this, digest it, and let's move on to the next one. Okay, so after you've taken some time to try and solve this problem, let's solve it together now. So we'll first redraw the diagram down here. We know it's a square, so this part is 90. And this is the midpoint, let's define this part as x. And we also know that is 45. And what we're trying to find is the change of this length here. Let's label this as S, right? So let's find stationary. When he is on this point, what is S? Sorry, there's no squared here. So you should get S is around 62, right? Okay, now what is constant? Well, what is always constant is 90 here. 90 here never changes despite where the person moves. So let's write our expression down. And notice we cannot use 45 because x is changing. Alright, divide both sides by 2. Okay, this is our final equation, and all I have to do now is plug in numbers. So we know S is 100.62, and we know this part is 24. So, and we know X at this point is also 45. So, it's 10.7 feet per second decreasing. And that's our solution to part A. Now for part B, let's come back to our original diagram. You should be able to use logical sense that that this part is the exact same as this part. So this part B answer is also. However, in part B, this part is increasing. And that's our solution. Okay, this is our final question. This one is relatively simple compared to the others, but I suggest you use what I've taught you of drawing diagrams, finding what's constant, what's always changing, to eventually arrive at the final solution. Okay, let's start. So we have our distance here. So this is our diagram, right? We know given this part is 1, and at this point, this is 8, right? So we know, let's put this part as L. L squared equals 8 squared plus 1 squared. So L equals 65. All right, now let's write our expression in terms of when the boat is moving. And let's define this part to be x. All right, let's cancel out the 2's. We know x is 8, dl over dt is 1, and L is root 65, right? So that leaves us with and that's our answer. So as you can probably see by now, the calculus and the algebra in these type of questions is extremely simple. What's hard is finding what's constant and what's changing. In this particular question, you have to realize that this 1 here is always constant, and L and X are changing. That's the hardest part of related rates.